Topic 8A, Introduction to Optimization. In this lecture, I'm just going to be introducing the concept of optimization. We won't necessarily be talking too much about the algorithms themselves. That's for following lectures. More here, what I'd like to do is talk about the merit function. Because when we're optimizing something, maybe it's a device, and we have multiple considerations, we have to simulate that device or analyze that device and come up with a single number that tells us how good that design is. And so that's the merit function. And in my experience, within a week or so, you can get just about any algorithm to work, but you'll work your entire PhD doing the merit function. So that's worthy of some discussion. And there's one special thing that we do a lot in our group that we call the rectangle algorithm. And I'll explain what that is, but that's really intended for calculating the merit function. It's not part of simulating a device or even the optimization algorithm itself. It's just one of the ways we come up with this single number. So let's dive into this. So what is optimization? Well, we'll have a function, and it probably depends on multiple things. Here I'm just showing something that depends on X and Y. But X and Y could be real things. They could be the dimensions of a device, material properties, and somehow we want to tweak all this in a way that either maximizes or minimizes that function. We can optimize both ways. So even though we have multiple things, we have to somehow boil this down to a single number that tells us how good our design is. And so in this lecture, we will call that the merit function, but it goes by other names. Other places will call it a fitness function, a quality function, a cost function, and it all means the same thing. So let's think of an example to illustrate this a little bit better. Let's say we would like to design a diffraction grating. So we'll have a wave coming into our diffraction grating, and when it hits this periodic structure, it splits into, in this case, 3 discrete directions. And the power from that applied wave splits into those 3 different directions. We would like to design the depth of that tooth and the width of that tooth such that no power goes into that center mode. We call that the zero order transmitted mode. So that's our problem. Find F and D so that 0 power goes into that mode. So over on the right, we construct what we call the solution space. And so horizontally are all possible values of D, or the depth of the grating that we'd like to consider. And along the vertical axis are all the different possible values of F, or width of the tooth, that we'd like to consider. So in this 2D plane, every point represents a specific design. So if we look at this bottom left point, that is both a small value of D and a small value of F. So what we see is a very shallow, skinny tooth. Well, we could choose this other point, which is both a large value of D and a large value of F, and now we have a very tall and wide tooth. So any point in this plane represents a different design. Now, we could do what's called an exhaustive search. This is where we just set up, in this case, a big double for loop, and we simulate every possible combination, and we look for the best solution. Well, that can be very computationally intensive, and many times if you run an optimization, if you look at the time it would take to do an exhaustive search, it could literally take hundreds of years, which clearly we don't want to wait that long. We won't be alive in that long. So we would like to somehow more intelligently search this 2D space so that we don't even have to come close to doing a comprehensive search, yet we have a pretty good idea that we've converged to the best solution. And that's the point of optimization. So let's talk more about that. Now in this case, I've done the work for you. And I did actually set up a big double loop and did a comprehensive simulation of every single device design. And I plotted the merit function. And in this case, that merit function is how much power went into that zero order mode. And look how crazy that solution space is. And this is not necessarily a crazy device. This is very typical of what a solution space could look like if you were to plot it. And now we have to look at this and figure, well, where is the best solution? And well, since we wanted to have zero power go into our transmitted mode, we are looking for the smallest numbers, or in this case, the darkest values of blue. And we have multiple solutions here. Now, since we have multiple solutions, we might ask the question, is one of those solutions better than another? And the answer is yes, absolutely. And so all the other ones are called a local best. And very easily, optimization algorithms can get stuck into these local best solutions. And really, we'd like to search our solution space a bit more comprehensively to find which one is the absolute global best. And there's a lot of claims of different optimization algorithms being able to guarantee finding the global best. Well, if you don't know anything about your device and you're using an optimization that involves randomness in any way, the only way you know that you have the global best is if you've done a comprehensive search. And we already said we don't want to do it that way because we don't have time. So if you don't know anything about your device or the solution space, there's no way you can guarantee that you've converged to the global best without this comprehensive search. Now, I've done that here, so we could get the absolute best. This simulation probably took several hours to do each and fill in each point here. So now imagine we added just one more variable to that. Now we're talking about probably a few weeks to do a comprehensive search. Then imagine we add a dozen things. Pretty soon that comprehensive search is taking millennia, which we don't have time to do. And that's really where the optimization is needed. Okay, let's move on. So optimization algorithms can be broadly categorized into two different flavors, if you will. There is the direct methods and the stochastic optimization. The stochastic is involving randomness. We would like to search this solution space a bit more comprehensively, so we might sprinkle a few different random solutions around and maybe introduce some noise and they kind of buzz around the solution space seeking a best solution, somehow involving randomness, but clearly in an intelligent way to get something real done. Then there's the direct methods that don't involve any kind of randomness, and maybe we try one solution and we look at the gradient and we're constantly either walking down or up, depending how we're optimizing. Something like that's a direct method. So direct methods also include the complete search or the comprehensive search. And as I mentioned, if nothing's known, that's really the only way that we can guarantee a global best solution. And then, of course, there's these gradient methods. You've seen some of those in previous lectures, the Newton's method, for example, Newton-Raphson method. And in a following lecture, we'll talk about the Newton's method, which is really a neat little tweak to the Newton-Raphson method to turn it into an optimization algorithm instead of root finding. So we have direct and stochastic optimizations, and we'll talk about all of these. Some notes on optimizations, and maybe some of this is more opinion, but I really do prefer the stochastic methods when I know very little about my device or the solution space, and I would like to do a rather comprehensive search of the solution space. So for those, I tend to lean towards the stochastic or randomized methods. I hear a lot of claims about algorithms guaranteeing the global best solution, and you can't make that claim unless you know something about your device. Maybe you know the theoretical performance limit, and somehow you'll know when your algorithm has found that. But if you don't know anything about it, and you probably don't if you're doing an optimization, then you really can't make that claim. So only an exhaustive search can you really guarantee that you have found the global best. Now, there maybe is a difference between a scientist and an engineer here. An engineer is going to go into this where I need to meet these certain performance requirements, and as soon as I find a solution that does that, we're done as the engineer. We don't necessarily care if it's the absolute best. Now, the scientist might get a little more picky and really want to find that global best solution because that scientist might learn something once they're looking at that global best solution. In my experience, the direct methods are extremely fast, but they tend to be designed so that they're only finding a local best solution. So this is where you walk down the gradient to the bottom of a curve or the top of a curve to find a maxima or minima. So I tend to apply these when I have a pretty good guess as what the device should look like, and I just want to fine tune it. And the stochastic when I don't know anything. Sometimes I'll run a stochastic optimization, and as I start to converge to something, I'll switch over to a direct method and lock onto it real fast. And in my experience, you'll always hear people contrasting genetic algorithms versus Newton's method versus all those other things. All of these algorithms work, and really within a week or so, you could get any of these algorithms to work. If you practice at it, probably just an hour or so. But you'll spend your entire PhD working on that merit function. And the best optimizations, I believe that merit function has to evolve. Normally that merit function would start very loose and accept a lot of different things. And as you start to get some designs and you can start seeding your optimizations with designs that are relatively close, you can start tightening up that merit function, make it more picky and punish and reward your optimizations in more different ways. So the best optimizations seem to have a merit function that evolves. And in my opinion, that is worthy of much more conversation than the actual optimization algorithm itself. Okay, so let's talk about this merit function. Again, this is that one single number that somehow accounts for everything you want out of a design, turns it into a single number. So here we're looking at that solution space again that we talked about before, where we're trying to minimize the power in this zero order mode, or that little center diffraction order. So in this case, my merit function as a function of f and d, the width and height of that tooth, is simply just the transmittance of that zero order mode. And I plotted it there. Now we have several possible solutions. If we look at this, there's several areas with dark blue. Well, we probably would like to make a device that's a bit more robust to manufacturing so that we can goof on the manufacturing a little bit and still have a device that works. Well, we found the global best solution to be in this tiny little notch here. But any little deviation in our F and D values will throw that off and our device won't work anymore. However, if we look at this local best, that has a much wider region of dark blue. So we could have some errors in our values of F and D that happen in manufacturing, and our device will still work pretty good. So very often, we not only look at the number, but we look at, I guess, the bandwidth you'd call it, or the area over which that number's been optimized. So in this case, we could make the merit function the transmittance divided by the width of that transmittance, or the bandwidth. And again, in this case, we're optimizing by minimizing that merit function. We could just as easily turn this around to maximizing it by saying width divided by transmittance. So when you come up with a merit function, my point is keep thinking about it. There might be more to it. There might be more things that you want to optimize for. So let's say we have multiple things that we want to take into account. How do we tie all this together into a single merit function? Well, there's an infinite number of ways to do this, but what seems to work most consistent for me is essentially a product of all our different considerations. So for example, we might have a bunch of different considerations on the top that we label as A. These are things, let's say that we want to maximize those numbers, so bandwidth of a device or something like that. And if we have multiple considerations, we will multiply them all together. We might have numbers that in order to improve the device, we want to minimize those. So we'll divide by those numbers so that as they become smaller, the merit function becomes larger. And I use this a lot. So I'm multiplying and dividing things to combine multiple considerations. We can certainly add them. You could add them, then take the square root, all kinds of different ways. But I tend to fall on this more often than other things. Now we have to think, okay, we have all these different considerations tied into a single number, but it might be that some of those are more important than others. How can we sort of suppress the importance of one while still considering it, and then maybe enhance others? So one of the most obvious things we might think about doing is multiplying each of these considerations by some constant. And maybe if A1 is the most important, we would make A larger. Well, the problem is when we multiply all of this, these importance factors all come to the outside, and then we could ask, well, which one does that belong to? And in fact, it could belong to any of them. This is not a good way, or not a way at all, to convey the relative importance of these multiple considerations when we're multiplying them. Now, if we were adding them together, weighting them with little a, b, and c, that would be an option. But it's not an option when we multiply them together. So instead, I do things like raising them to exponents, taking the log, adding a constant to them, or hybrids of all of these. And I have an example following that'll illustrate how I've used all these things in combination. So these are my tricks for suppressing importance of some things. So a natural log of a number would tend to suppress its importance. If we raise it to an exponent, if that exponent is greater than 1, that would tend to enhance its importance. Something less than 1, it would suppress the importance, and so on. So here's an example that goes way back, some work I did many years ago. But we were looking at optimizing an antenna. Man, this is almost 20 years ago. Holy smoke, time flies. So the very typical merit function of the time, they wanted to make antennas that were broadband and efficient. So they'd multiply the bandwidth and efficiency together and get a merit function, and antennas were being optimized this way. So at the time, I wasn't an electromagnetics person yet. I was a signal processing and communications person. And I had been studying channels and coding and all these other things. And I realized, bandwidth and efficiency are not always equally important. More fundamentally, we want to maximize, let's say, the data rate of a communication link. And in that case, bandwidth and efficiency are not necessarily equally important. And so I felt we could do better with the merit function. So there is what's called the Shannon capacity theorem. And that's the equation at the bottom here. And the capacity of the channel, so think of that as bits per second, although there's a bit more of a story behind that, is the bandwidth, that's B, times the natural log of 1 plus the signal to noise ratio. And that'll tell us the theoretical maximum bits per second that a channel can support. And so right away, we see that bandwidth is outside of the log, and the signal to noise ratio, which is more indicative of the efficiency of the antenna, is inside the log and being suppressed. So the E term up here in our initial merit function, I would say should be suppressed compared to the B. So I decided to go with a merit function that was inspired by the Shannon capacity theorem. So this was my merit function, bandwidth times the log of 1 plus the efficiency. Why not signal to noise ratio? Well, we're just looking at the antenna. We don't really have any way to know what the noise is yet, but certainly the efficiency of the antenna would factor into the signal to noise ratio. So this is no longer the Shannon capacity theorem. It is just our merit function inspired by the Shannon capacity theorem to better convey the relative importance of bandwidth and efficiency. Well, we also wanted a small antenna. So I decided to divide the merit function by L, which might be the largest dimension of the antenna. And since we're dividing by L, a small size will tend to maximize M. So now we had an improved merit function inspired by the Shannon capacity theorem but now also with size in there. And we could also ask again, well, maybe size and bandwidth aren't equally important. I decided to ignore that at this point and just divide by L. But there's something else that can happen, and this happens a lot when you're playing with your merit function. And we could have an antenna of length, 0.00001. So we know the bandwidth will be horrible. We know the efficiency will be horrible. It will be a horrible antenna. But because the length is so small, the merit function will be really high, and we're locking into false solutions. And this is one of the reasons why we have to monkey with the merit functions as much as we do. So what do? Well, I decided to just add 1 to L at the bottom. So when L goes to 0, that denominator stays 1. And in this way, we sort of weakened or suppressed that artifact. When L approaches 0, we get this infinite merit function. So we fixed that. So this is another way to enhance and suppress things, adding a constant to certain variables. So that was my final merit function for this antenna optimization, and it worked well, and we actually got better designs than any of the other antennas they'd been designing to date. Okay, so in my group, we do electromagnetic simulations. So we'll simulate a device and we'll calculate things like reflection versus frequency. And so maybe we're trying to design something that's a very broadband reflector. So we have to not only look at how reflective it is, but over what range of frequencies it is reflective. And so this is a very common thing we ended up doing, and we came up with what we call this rectangle algorithm that I'll share with you as an example of one component of calculating a merit function. So we might simulate a device and see something like this. This is reflection versus frequency. And then we ask a question, well, how good is that? Over what bandwidth is it reflecting? How good is it reflecting? How do we even determine that? And so basically we came up with an algorithm where we fit a rectangle under that curve, and we look at the width as the bandwidth and the height as the overall performance. But how do we do this? So our merit function in this case will be bandwidth. We probably want this to be broadband. If we didn't, then we might divide by bandwidth to punish it for being more broadband. And sometimes we actually want narrowband things. For example, if you're designing a filter to lock a laser, usually lasers want to be very, very narrow line width. If we're making a broadband reflector, in this case, we're going to say we want it to be very wide. Performance in this case is the height of that red curve. It's the amount of reflection. We want the reflection to be very high and over a wide bandwidth. So the merit function here would be the bandwidth times this performance metric, which would be reflection in this case. So our merit function is the area of that rectangle. But we have to think about how do we figure out where is the biggest rectangle under that curve. And so that's what this algorithm does. So going back to the original curve we were looking at, there's two rectangles here, and they look kind of similar in area. Which one's going to be better? And is there another rectangle somewhere else? How do we determine this? So this is the algorithm that we came up with. So we decide on a merit function, we simulate the device, calculate its spectrum, and at that point we figure out where the biggest rectangle is. How do we do that? We set up a loop over the spectrum. And we have animations of this following it, so don't expect to absorb everything from this little step-by-step outline here. So we set up a loop and we go point by point across our spectrum. For every point, what we want to do is look left until we hit that spectrum line again, and essentially what we're doing is placing the left side of that rectangle. Then we seek right until we hit our spectrum again, and that places the right side of the rectangle. Now we have a rectangle that's been fit to that curve, and the top is maxed out against that spectrum curve. From there, we calculate the merit function as the area, or perhaps we weight bandwidth and performance in some other way. And we do that for all points. And the point that had the biggest rectangle is the winner. And that rectangle is where we have the best performance of the device. So let's look at some animations to make a little more sense out of this. So here's an animation where we're going not point by point, just for speed, I'm going a little bit further. But for every point where you see that vertical dashed line, the first thing it does is look left. And then the second thing it does is look right. So the looking left in this case was instantaneous because it was sitting right against the curve, but it's looking right and it's going point by point all the way to the right until it hits the spectrum again. And then that would be the rectangle. It moves to the next point, looks left. You didn't see much there because there is no left, and it seeks right till it hits the spectrum curve again. So for speed, we're going in large increments here, but in reality, your algorithm would go point by point. Now that we're on the downward slope, you see the seeking left, but the seeking right is almost instantaneous. Now that we're sitting at a valley, you can see both. We seek left, we seek right, and we fit the rectangle. If we didn't seek both ways all the time, we would have missed that. Here we're at another valley again, and so you can see both the seeking left and seeking right. If we only ever sought right, for example, when we're sitting at a valley, the rectangle here would be half what it should have been. So we always have to seek left and seek right. And so while this is running, the idea is that you're storing the point that had the biggest rectangle, and you're remembering where that was. Now in the remaining animations, what you're going to see is you're not going to see the seek left, seek right anymore. You're just going to see the rectangle associated with each point. You'll see that when we get to it. So I'll start when this animation finishes. So in this animation, I'm just trying to convey the seek left, seek right. Almost done, and then we can move on. Maybe I should have made this faster. All right, so that's it. We started over again, but I won't play this. If you want to see it over again, go ahead and rewind the video. Now we're looking at the same curve. And what you see now, we're not showing you the seek left, seek right. The green rectangle is the final rectangle from that seek left, seek right algorithm. And the red rectangle is the biggest rectangle that is found in the sweep so far. And of course, if you're not displaying graphics, this runs very, very fast. And we go point by point, seek left, seek right, remember the rectangle, and find the largest rectangle. So this is the algorithm when our merit function is width times height, where we're literally maximizing the area of that rectangle. So we might ask, what does this look like if we suppress the importance of width or height? So let's go ahead and watch this max. I believe that is the maximum rectangle for the width times height merit function. Let's go to the next one. Now we are suppressing the importance of width and enhancing the or amplifying the importance of height. So what you'll see now is I'll call it the largest rectangle, but it's no longer purely area anymore. But the best rectangle it's found has now preferring height over width. And I believe that rectangle that just left behind is the best that this particular merit function will find. In our application, maybe it's more important we have strong reflection than it is broadband reflection. Okay, let's look at this the other way around. Now let's suppress H and enhance the importance of W. So that's what's happening here. We've enhanced the importance of the width of the rectangle and suppressed the importance of the height. I have a feeling this rectangle that we're looking at now is going to be the best rectangle because we've amplified the importance of width. So here, bandwidth might be more important to us than what the reflection is. As long as we reflect something over that bandwidth, maybe that's satisfactory to us. Okay, so hopefully you get the point. We can do any of these things in any combination that we want. But this rectangle algorithm in our research, we use a lot. Just to give you an idea of what these look like, this is an output of or I should say it's an intermediate result of a real optimization that we run. And we don't pay too much attention to dressing up the graphics. This is more just our dashboard as an optimization is running. But we're looking at reflection for something called a guided mode resonance filter. And you can see where we're fitting rectangles to this to figure out over what bandwidth they're reflecting or transmitting. So this is real data from real devices from a real optimization. And in this case, the merit function was the absolute value of transmittance times bandwidth.